is Zoran Krunic. I'm Senior Manager of Data Science, Research and Development at Amgen. So I'll talk about quantum kernels for health science data, in particular, reproducibility and variability challenge in small data sets. So important small data sets in health sciences. There are a couple of reasons. We have lots of rare diseases which lead to very small data sets. And so that's where you can expect maybe a couple of hundred samples at most. Small clinical trials as well, especially phase 1 and phase 2 clinical trials, often will have a very small number of patients, sometimes 50, 100, 150. And then finally, one of the areas that's of more and increasing interest today is personalized medicine, where we also expect to have small data sets because of the difficulty collecting comprehensive data sets. Now, when we look at kernels, why do we use them? They're not anything new. They've been used in classical machine learning for a number of years. They provide nonlinear separation by mapping data into high-dimensional spaces. They're efficient, and they have a couple of other properties and features that we like. And so they've been part of the models like SVM, support vector machines, for a number of years. And not just in health sciences. I think in some of the financial industry, SVM plays the role as well. Now, in quantum computing, we are presently limited to small data sets just because of the ability to encode data into hardware. The noise and everything else limits us to usually in the range of a couple of hundred samples. However, that actually matches the previous discussion of why we care about small data sets. So that's actually not a constraint today. Now, out of those two things, we get to the problem of variability. So normally in classical machine learning, we would take your data set and split it in train and test roughly. There may be a little bit more nuanced processing, but that's roughly the approach. You have the training, you train your model, then you fix it, and you make prediction on test data set, and you see what the accuracy is. And you usually would do it 3, 5, maybe 10 times to explore that with different random number seeds or some other way. But basically, you want to get different pairs of train and test data sets to be able to tell what's the variability at the end accuracy or whatever is the metric that you're using to evaluate your model. Now, if you're somewhere in 20, 30, 50,000 sample range in classical machine learning, usually that difference is going to be minor, a couple of percent. You'll still do it maybe as a due diligence, but really won't make any practical difference. However, when you go on small data sets of 100, 150 samples, that becomes a problem. You're going to see much bigger variability. The detection of outliers becomes quite difficult. You're running a much higher risk. Actually, it's almost guaranteed that you're going to overfit on small data training size, and so you're going to have to do regularization. So lots of problems happen, and we are very interested in that area because there is a practical application for small data sets. This is not a toy case. This is actually something that has immediate and practical value. Now, these are kernels on the left. This is the classical one, often used radial-based function, or RBF kernel. It basically measures the closeness between two data points. That's been, again, talked about a lot, and so I'm not going to go into details. On the right-hand side, you see what's called the kernel trick. Why the kernels and the mapping is so important, because you would take a problem on the bottom left that you have a two-dimensional area, and you can see green and red spots that you want to separate. It's difficult, but if you add third dimension, you might be able to do that much more efficiently. And so that mapping it to high feature range holds lots of interesting features and properties and could be exploited. Now, this is all, of course, classical. If you go to quantum kernels, what's different? Well, difference is, of course, they're happening on a quantum computer. They measure the similarity of two quantum states, and we use feature maps to do the mapping into the high-dimensional spaces. And then once we are in quantum, in Hilbert space mathematics, we have superposition and entanglement to work with and take advantage of. Now, these are 3 use cases I'll talk about briefly today. And there are 3 hyperparameters, if you like, in that 3D plot there. So one is number of samples, which we're keeping down at about 50, 100, 150 to 300 range. Top features, 5, 10, 15, 20. And the number of shots at the quantum run, either at the QPU level, in this case, is 1K, 2K, and 8K. The blue box case is the one we worked during our collaboration with IBM. And I'll talk a little bit more about it in the coming slides. The other 2 are slightly different data, but all medical data, and even smaller range of samples. There are other hyperparameters we could talk about, like type of imputation, type and range of scaling and centering, for example, which is done, and numerical versus categorical features, what difference that makes, NLP features as well, if they are part of the model, and they're increasingly becoming part of most models. But we focused on these three here. So first use case is persistence of rheumatoid arthritis patients on biologics. Means measuring when patient starts biologic medication for arthritis, how long will they persist or stay on that medication. It's high-value target. It's 10 million plus patients worldwide, over 1 million US. It's 30 billion plus annual market just for biologic medications. Classically, we've done lots of machine learning in clinical and healthcare context and combined it with clinical healthcare data. Now we are adding quantum computing and trying to see how that changes the game. Now, why that specific use case? So when we started quantum computing project collaboration with IBM, we were at the end of the prior project, which was really classical machine learning in that described area. And it started with Optum EHR data set, electronic health record data set. Didn't have claims data, just prescriptions and all the other laboratory measurements, doctor visits, and so forth. We built about 10 plus different models. There are about 30 variations of those models. We worked with clinicians, rheumatoid arthritis specialists, and people from sales and marketing for a year and a half, regular meetings. And we managed to fully understand the context in which data is created. And it's really important. If you blindly take a data set and run it through models, you're running a serious risk of making mistakes. For example, when it comes to how you impute the data, it's known that if you have missing data, and EHR data often has missing data, you have to understand why, otherwise you're going to make a mistake how you impute it. For example, it's known that healthier patients have less data points, and so if they miss something and you impute it from patients that have more data points, you're risking making a bias towards those that are less healthy. And so you want to be very careful about that. So we understood all of that and presented that internally, and we were very confident with what we achieved. At that point, the quantum computing project started, and so it was kind of a quantum-ready situation where you understand everything about data, everything about what you can do classically, and now you're going to move into the quantum domain. What's the connection between classical and quantum? We spent some time at the beginning, this was about 2 years ago, trying to understand when we started, how do we put this together? And so one of the things that comes up is the number of samples. The classical model had 16K samples. Over 500 features, we had to bring that down to about 300 and about 20 features now. Number of features is important because if you're using a model like SVM or QSVM in terms of Qiskit and IBM platform, it means that one feature will be mapped to 1 qubit. Doesn't geometrically or mathematically work directly that way, but at the end you can think of it that way. And so what it means that if you have 20 features, you will need 20 qubits. We had 27 qubit machine, IBM Q Dublin, which was dedicated to us for about 5 weeks. And so we came up with the geometry of the problem that we've thought we can fit into the time, QPU time that we had available. 20 features may sound little compared to 500 when you start, but the reality is in most models like this, top 15 or 20 features will carry about 90–95% of your accuracy. The rest of the features tails off, and it's not really important. So, and you can test that by taking the top 20, and if you figure out the right way to call those top 20 features, you will see that that model will be probably 95% of the accuracy of the model with 500 features. That's often like that. And so that was the connection we made and moved forward with 20 qubits out of 27 qubit machine that we had available. Now this is a very simplified version of the hybrid pipeline that's often used. On the left side, you have that smaller box, general data preparation. In reality, it's really a big box that has a lot of things that happen inside. The hypothesis that I have right now is that that's generic to both classical and quantum models. Does that hold over time? Do we find that maybe we need to massage data a little bit differently before going into quantum model? It's possible, but right now that's the assumption that we make. Then you get into the second stage, which is right before you go into the model, you're going to do what's called scale and center, and that's not necessary in random forest or XGBoost models, which are tree-based models, but SVM and neural networks often you will do that. And the reason is simple. If you look at the features that come into EHR data set, you have, for example, cholesterol, which ranges of 150, 200, 300, and you have something like BMI, body mass index, which is 20, 25, 30, so the range is 10 to 1. That's a problem for models like this. You want to bring them into the same range. Usually it's -1 to 1. It doesn't have to be that, but usually that's how it's done. Now in quantum, what we've done, we scaled it to -pi½ to pi½ pi being the 3.14, of course. And so that was a recommendation from one of the research papers in quantum computing right at the time where we started this, and so we took that recommendation. We didn't explore what happens if you do -1 to 1 or something like that. Of course, those are all hyperparameters to the process, but they require you to basically go through the whole QPU process again, and that's not simple. Another interesting element here is potentially using QC for imputations. Imputations are huge area with missing data that's part of this story all the time. And our colleagues from QCVR published a paper recently showing how you can use quantum computing potentially for that. And I think that's really something that I haven't seen in much of the research. I think that's a great area of research because imputations are extremely important. And it comes down to distributions of underlying data where you're going to sample the missing data from. And so I think it makes a lot of sense to look at the quantum in that area. And then you move to classical versus quantum kernel calculation, and then bring it back into the scikit-learn pipeline. And at the end, what we got was that F1 score, which is what we chose as a metric because it allows you to track imbalanced binary classifications as well. The quantum did better than classical across most of the landscape of the features and training samples that we explored. Now, the other two use cases, I'll kind of bring them into one discussion and one presentation, is we are looking at very small number of samples. This is cardiology, but it's a binary prediction, slightly imbalanced, but not terribly imbalanced, which is important when you're in a small range of data, small samples. It's very hard to deal with 10 to 1 imbalance, and so we picked up something which was pretty much balanced. The variables are typical cardiology variables. I'm not going to spend much time on that, but that's the part where we wanted to predict the outcome, which is 0 or 1, basically. Now, this is a typical flow of classical machine learning processing. You have your train process with cross-validation. You manage your random number seeds carefully. There are nuanced situations there when it comes to scikit-learn, for example. There is the different geometry of how you can do cross-validations, different options. But that's where kernels come in place when you calculate the train dataset kernel. Then you can do hyperparameter tuning, which is often required, or HPO, hyperparameter optimization. Then you move into probability calibration if you want to do so. Sometimes it brings a little bit of advantage, sometimes it doesn't, but it's principle, it's a step there. And then your final test on unseen data, that's where you calculate the kernel again, classically or in quantum, on your final test data set, and you have the metrics. And then you repeat this process with different random number seeds 5 to 10 times if you can, and compare the results. Now, this is a busy slide, but basically what it shows is on that data set, we had 150 samples in the train data set. Test was 50 samples. We did a QPU simulation on a public instance with 7 shared mode on IBM Cloud with 7 qubits. We did simulation, both in Qiskit, and then classical processing. And we can see the purple line is connecting 10 different train test splits, and final accuracy on each of those varies, as you can tell. That's the purple line. The orange line is the simulation, and the blue is the classical. And what we can see is the classical did slightly better than QSIM or QPU do, but very little, a couple of percent. What's interesting, though, and very important is that especially the simulation had a standard deviation or variability much smaller than classical, 0.043 versus 0.66. And so I think that's important, could be even potentially more important than maybe 1 or 2% of lower accuracy. The confusion matrices also look very good in both classical and quantum. That's something you always need to look at, because if you have something which is imbalanced, you can have a model that's going to predict all zeros, where you have 70% zeros and 30% ones, and it looks like you have 0.7 accuracy, but you really don't. That's a degenerated case that you don't want to have. And so you need to play the weights on your false positives and false negatives in such a way that you bring the matrix in the place where you want it to be, and that's the function of the cost of those false positives and false negatives in the particular deployment scenario. It's very hard to generalize it. You have to make some assumptions on that. Now, one thing that's also important to mention here, these differences are not the differences in the kernels, let's say a simulation versus QPU. That's not difference in the kernel itself. That's just the kernel is just a two-dimensional NumPy array, lots of floating point numbers between in a small range. What you are really measuring is aggregate impact of those differences as it flows through the model and comes up at the end with your metric of choice, which is in this case F1 score, and gets transformed to the SVM model and all the geometrical and, if you like, linear algebra transformations that happen inside. Now, putting those two next to each other, so we did better on F1 score on the bigger grid, most of the part of that grid. When we moved here, we are slightly under the classical values, but we have smaller variability. On the top left there, the bigger grid, we only had 2 train test splits for each coordinate because we didn't have enough capacity to do more. So really, we don't know the variability in that range. We just know the averages. Here, though, we go deeper into train test splits averages, measurements in, and we can see that we have quite a bit of variability, somewhere in the 10 to 15% range. And that's the part we are talking about. We would like really to make that much smaller because that's going to be important for being able to deploy these kind of models. I looked at the distributions of each of the features separately and looking potentially at outliers to see what makes quantum better in some splits or some data and not the others. Because if you look what happens here, we really have train test split. And if you look at the train and test, they're non-overlapping, but they're all part of the same data set. And so when you see a differences between 100 samples here and some 100 samples there, one does better in quantum, the other in classical, the question is why? It's going to be in the data, right? Because everything else is the same. And so individual features, I looked at that. I didn't see any differences, any outliers that would imply that quantum was better here and classical there. It's worth a second and maybe a third look, but which I will do. But I think, and this is the discussion I had recently with Grant, who is the co-founder of Blue Qubit, that it's probably joint distributions that we are looking between these 7 variables, or maybe subset of those 7, that make a difference and somehow make quantum work better than classical. What's really good here is that we actually have a reproducible data set that will consistently show advantage or disadvantage, so we can drill deeper and find out what exactly makes quantum work better in which cases, and you can potentially then fork your processing and say, okay, this should go to quantum and this should go to classical processing. Now, the next step, going even further, is to take the first point on top left, which was one here on the purple, which was 0.74 F1 score, and you take that one and you fix everything else, and then you take your test data set, same fixed test data set, which in the first run showed accuracy of 0.746 F1 score, and run that 10 times through the QPU just to look at how much variability you get out of QPU noise. It's important for reproducibility. We know that that's a very important factor. We can manage all the rest carefully through the random number seeds control and get reproducibility down to 10 decimal digits. Now, in QPU, we can't quite do that yet because of variability, and I was afraid that we were going to get large span. Actually ended up being quite well. I ran 10 runs. The one didn't finish, but these 9 are shown there, 0.727, 741, all the way down to 763. So very small range in 10 different runs of the same data set. The standard deviation is 0.01. Average is exactly practically what we had there. And so you have a 5 times smaller standard deviation compared to the deviation that comes from train test splitting, right? And so that kind of makes sense intuitively. The range is really good, and so I was very happy when I was able to see these results. I think it's quite promising. Where you go from here, I think there are a couple of ways to potentially improve this. One is going to better, newer IBM instances like 127 QPU Eagle, for example. The other one is to look at the software approaches that Q-Control and Blue Qubit are doing. I think that Q-Control just announced the collaboration with IBM in that direction, so maybe we can get some improvements. Very interesting architecture from here on neutral atom architecture. So these are all possibilities that we can rerun this and see if that makes a difference and what we can learn from that. And so if you put all this together, this is how the whole journey looks like, going from the big grid with small, only 2 splits, to the second case where we take 1 coordinate, slightly different data, but also medical, and do 10 different splits and explore all 3 QPU, QSIM, and classical, and then take one of those points and run it 10 times just to look at the variability of the noise. So you can see that standard deviation gets reduced as you go through this process. And so now I have a fairly good feel in my head what is it I can expect from at least this type of a data in terms of variability. And we have a solid data set where we can start looking at those joint distributions and perhaps find out what really makes QPU better versus classical in some of those data cases. But I think it's going to be potentially just a couple of rows out of 100 could make a 3 to 5% difference. So I think it's a tangible thread that we can pull on and follow the path and see what happens. So thank you. That's the end of the presentation.